The temperature outside your window right now, whatever it is not trying to kill you. The infrastructure surrounding your body at this moment, the insulated walls, the climate-controlled air, the engineered textiles wrapped around your skin, represents 10,000 years of accumulated thermal management technology. Remove all of it. Strip it away entirely. Now place yourself on an open Eurasian steppe, latitude 55 degrees north, during the last glacial maximum, approximately 21,000 years before the present moment. The ambient temperature has dropped to negative 47 degrees Celsius. The wind is moving at 30 kilometers per hour across a landscape with no trees, no natural shelter formations, and no possibility of modern intervention. You have approximately 12 minutes before the onset of severe hypothermia begins compromising your neurological baseline. You have perhaps 40 before cardiac arrest. And yet, a population of anatomically modern Homo sapiens not only survived in that environment, they thrived, reproduced, created art, developed complex social hierarchies, and engineered solutions to thermodynamic problems that, when examined with clinical precision, reveal a cognitive sophistication that the word primitive does not merely fail to describe, it actively insults. This is not a story about cavemen huddled around fire. This is a story about the most demanding engineering challenge in human history, and the forgotten genius of the people who solved it with nothing but biological intuition, observational mastery, and a neurocognitive architecture, identical to the one you are using to process these words right now. To understand what Ice Age humans actually built, you must first understand the physics they were operating against. The Laurentide and Fennoscandian ice sheets during the last glacial maximum had depressed global mean temperatures by approximately 6 degrees Celsius relative to pre-industrial baselines. That number sounds modest until you understand that it represents a planetary-scale reconfiguration of atmospheric circulation patterns, precipitation regimes, and biome distribution. The mammalian megafauna that shared the landscape with these humans, the woolly mammoth, the cave lion, the megaloceros, the woolly rhinoceros, were themselves evolutionary responses to those thermodynamic pressures, organisms that had spent hundreds of thousands of years accumulating biological insulation strategies. Homo sapiens had perhaps 100,000 years of African evolutionary history behind them. Their subcutaneous fat distribution, their surface area to volume ratio, their baseline thermoregulatory physiology was built for the savanna, not the periglacial steppe. The engineering gap between what their bodies could handle and what the environment demanded was not a minor inconvenience. It was an existential chasm. What they built to bridge that chasm was not primitive. It was, by any honest engineering metric, revolutionary. The first and most foundational technology was composite textile construction. Archaeological recovery from sites including Sungir in Russia, dating to approximately 34,000 years before present, and Dolny Vestonis in the Czech Republic, dating to approximately 26,000 years before present, has revealed direct physical evidence of woven and twisted plant fiber. Alongside the skeletal remains of individuals buried in garments, requiring an estimated 3,000 to 5,000 individual beads of carved ivory, sewn into layered clothing assemblies. Those beads are not decoration in any superficial sense. Each bead represents a perforation through dense mammoth ivory, achieved with stone microliths operating at precise angular tolerances. The functional purpose of that bead distribution is thermal insulation management through layered dead air trapping. These garments were operating on the same thermodynamic principle as modern Gore-Tex and Thinsulate composite systems. The layering created microenvironments of trapped air between fabric surfaces, reducing convective and conductive heat loss across the body's largest thermal radiation surface. The cognitive leap required to understand that trapping still air against skin reduces thermal energy dissipation, and then to engineer a material system capable of achieving that at scale, is not the cognitive leap of a primitive mind. It is the cognitive leap of an applied thermal physicist working without instruments, but with something arguably more powerful: direct sensory feedback from a body that would die if the solution was wrong. The needle changed everything. The eyed bone needle, recovered from multiple Siberian and European Upper Paleolithic sites, represents perhaps the single most underappreciated engineering achievement in human prehistory. A modern sewing needle is a precision instrument. A bone needle carved from the fibula of a bird or small mammal, with a perforation of less than 1 millimeter in diameter drilled through its head using a stone burin, is also a precision instrument. The manufacturing tolerances required to produce a functional eyed needle without breaking the shaft during perforation demanded an understanding of material stress mechanics, grain orientation in bone tissue, and force application geometry that is entirely non-trivial. These needles enabled the construction of fitted, tailored garments, clothing that conformed to the three-dimensional geometry of the human body rather than simply wrapping around it. Fitted garments are thermally superior to draped coverings by a significant margin because they eliminate convective chimney effects at the collar, wrist, and ankle openings. Ice Age humans engineered the fitted garment. They understood, through empirical iteration refined over generations, that the interface between garment and skin needed to be sealed against wind penetration at every anatomical junction. That is not primitive sewing. That is applied fluid dynamics in the context of a wearable thermal management system. But garments alone could not solve the full engineering problem. The human body at rest generates approximately 80 watts of metabolic heat. During moderate physical activity, that output rises to approximately 300 watts. During extreme exertion in cold environments, briefly higher. None of that output is sufficient to maintain core temperature in a negative 40-degree wind environment without a fixed thermal enclosure, a structure that reduces the effective temperature differential between the body's heat output and the ambient environment. They needed buildings. And they built them from the only structural material available in a treeless paraglacial landscape, the skeletal remains of the megafauna they hunted. The mammoth bone dwelling represents one of the most remarkable feats of structural engineering in the entire prehistoric record. Sites including Mezhyrich in Ukraine, dating to approximately 15,000 years before present, have been excavated to reveal circular and oval structural foundations constructed from the interlocking mandibles, femora, scapulae, tusks, and cranial vaults of woolly mammoths. The Mezhyrich site alone yielded the remains of approximately 95 individual mammoths incorporated into 4 separate dwelling structures. The largest of these structures had a floor area of approximately 24 square meters and a reconstructed internal volume sufficient to shelter a multifamily social unit through an extended glacial winter. The engineering of these structures was not random bone piling. Physical analysis of the assemblages reveals deliberate interlocking strategies. Mandibles placed jawdown in alternating rows to create stable foundation courses. Long bones used as vertical uprights socketed into ground permafrost. Curved tusks employed as spanning members across doorway openings, because their natural curvature distributes compressive load more efficiently than a straight beam. Scapulae, the broad, flat shoulder blades of mammoths, were used as roofing tiles, overlapped in a manner directly analogous to modern clay tile or slate roofing systems, shedding precipitation and wind while maintaining structural continuity. Over this bone armature, Excavated evidence and thermodynamic modeling both suggest coverings of processed mammoth hide, staked and lashed to the bone frame with sinew cordage, creating a composite wall assembly with an effective thermal resistance value sufficient to maintain interior temperatures significantly above ambient, even without continuous fire input. The fire itself was engineered. This is a point that deserves particular emphasis, because the controlled combustion systems of Upper Paleolithic humans were not simply fires. They were fuel-managed, ventilation considered, functionally specialized thermal systems. Excavated hearths from sites across the European Upper Paleolithic show deliberate construction, stone-lined combustion chambers that concentrate radiant heat output and protect the combustion zone from wind disruption, ash management patterns indicating regular fuel addition cycles rather than single ignition events, and spatial positioning within dwellings that reflects an understanding of convective heat distribution. The hearth placed such that rising warm air circulates through the occupied zone before losing energy to the structure's upper volume. Bone was a primary fuel source in treeless environments, and the caloric density of mammoth bone marrow fat, when used as a combustion substrate in conjunction with the structural bone itself, provided a sustained, high-temperature heat source that modern replication studies have confirmed can maintain a small enclosed space at habitable temperature during ambient conditions of -30 degrees Celsius or lower. They were not warming themselves by accident. They were operating thermally managed enclosed environments with deliberate fuel cycling and spatial heat distribution. The cognitive distance between that practice and modern central heating is one of materials and scale. The underlying system's thinking is identical. Food storage and caloric infrastructure present an equally sophisticated engineering story. The periglacial environment, while lethal in its thermal demands, offered one resource in extraordinary abundance: meat. The megafaunal biomass of the last glacial maximum Eurasian steppe represented a caloric density per square kilometer that may have exceeded that of any subsequent ecosystem in the region's history. But hunting a woolly mammoth, an animal massing between 4 and 6 metric tons with a neurological threat response system refined by millions of years of predator pressure, is not a casual undertaking. It is a systems engineering problem involving force multiplication, behavioral prediction, terrain exploitation, and coordinated multi-agent execution. The spear thrower, or atlatl, recovered from multiple Upper Paleolithic sites, is a lever-action projectile amplification device. It extends the effective length of the throwing arm, increasing the angular velocity transmitted to the spear shaft, and thereby increasing both range and terminal kinetic energy by factors of 2 to 3 relative to hand-thrown spear performance. The engineering optimization of atlatl geometry, the precise balance point, the hook depth, the flex characteristics of the throwing board, represents applied mechanics developed through empirical iteration across generations of use feedback. These were not lucky accidents of carved wood. They were tools refined to functional precision through systematic performance evaluation, the same iterative design methodology used in modern product engineering. Cold environment food preservation was managed through the exploitation of permafrost as a natural refrigeration system. Excavated storage pits at multiple Upper Paleolithic sites show deliberate excavation into permafrost layers, with evidence of cached faunal remains at depth sufficient to maintain temperatures below the threshold of bacterial proliferation. They built refrigerators, dug into the ground, lined with bone and hide, sealed against scavenging predators, and exploiting the thermodynamic stability of permafrost as a passive thermal management medium. The conceptual framework required to understand that underground temperature is more stable than surface temperature, and to exploit that differential for food preservation at scale is not the conceptual framework of a mind operating below modern cognitive standards. It is applied environmental physics. What does all of this mean for our understanding of human history? It means that the cognitive revolution, the emergence of fully modern human behavioral complexity, arrived not merely as art in cave walls or figurines in limestone, but as a comprehensive engineering intelligence applied systematically to every domain of physical survival. The Homo sapiens who endured the last glacial maximum were not waiting for civilization to begin. They were practicing it in the most demanding laboratory the planet has ever produced, with a rigor of empirical problem-solving that left physical evidence sufficient to reconstruct their solutions 20,000 years later. The thermal engineering embedded in a Sungir burial garment, the structural mechanics of a Mesurich mammoth bone dwelling, the ballistic optimization of an Upper Paleolithic atlatl, these are not the products of intellectual infancy. They are the products of a neurological architecture operating at full modern capacity under conditions of absolute selective pressure, where every engineering failure was lethal, and every successful innovation propagated forward through the population because it worked. The ice did not make them primitive. The ice made them extraordinary. And the distance between what they built with bone and stone in -40 degrees and what we build with steel and polymers in climate-controlled offices is not a measure of cognitive superiority. It is a measure of accumulated time. The intelligence was always there. It was forged in the cold,